So for this section, I'm creating two technologies. One of the technology videos is just going to be about Excel and the idea of using Excel to calculate these combinations that we're using. And then also showing, going through these examples and showing how to type it in all at once. So there's the Excel video where you can see these examples. There's going to be a second technology video where I go through GeoGebra. Again, it has very nice visuals and shows how these are calculated. And with GeoGebra, we can kind of bypass these formulas. If we know the scenario, we know these probabilities that we're looking for, GeoGebra will calculate these numbers for us. And in a more accurate way, there might be some rounding here, so it'll give more accurate values. But what GeoGebra is going to use is this scenario right here. So this next page we're going to go examples, and it's going to go kind of quickly because I'm just going to use the outputs from GeoGebra. However, be sure to maybe watch the GeoGebra video before you try this next page, so you can kind of double check that you're getting the same answers out from GeoGebra. But when it comes time for GeoGebra, remember you're going to want to think about this number of trials and probability of success. So with our example here, we're going to have an Olympic archer who hits the bullseye 80% of the time. Assume each shot is independent. He's going to shoot 6 arrows. So our information that we're getting here, we have this probability of success of 80%, which means we have a probability of failure of 20%. And then they tell us we have this number of trials, 6. So if we have our variable, say we wanted to define the model, x would be the number of bullseyes out of 6 arrows. So that's our number of successes out of our n trials, and how this is going to be defined. So just to make sure that it's binomial, what we want to think about is there's only 2 possible outcomes. He either makes the bullseye or he does 2 scenarios. We have independence, which means that 80% also isn't going to change. Each arrow he shoots, that's going to stay at 80%. And then we also have our set number of trials that we're looking at here. So that means we have a binomial model where we have 6 trials and a 0.8 probability of success. So this is first scenario, and this is going to kind of mix in our old probability rules as well. So the probability his first bullseye comes on the 3rd arrow. So notice that this has a specific sequence of events. He's going to make 1 bullseye, but it has to be on the 3rd arrow. So that means this calculation, we need failure, and then failure. So it's kind of like the very first example we looked at in this section, where it tells us a specific sequence. So with this, we don't need to use the binomial formula here, because it tells us exactly how it should happen. So this, we'd have 0.2 times 0.2 times 0.8, which is a 0.032. So there is a 3.2% chance his first bullseye is with the 3rd arrow. This one, not binomial there. For part B, he misses the bullseye at least once. So this one's kind of tricky because this probability of miss at least once. So what that would be saying is, what's the probability he misses it once, or misses it twice, or misses it 3 times, or misses it all of the times? So with this, we end up with way too many scenarios. If we start thinking about the or, like probability of miss once, plus probability of miss twice, plus probability of miss 3 times. Whenever you have this probability involving at least once, something that's going to happen is only one scenario is going to be left out. in that we pretty much want every scenario for missing except for the case where they miss none of them. So what we can do is use the complement rule. We take our 100%, and the only thing we want to exclude is this probability of no misses. That's the only thing that's excluded from this idea of at least once, because miss once, miss twice, miss 3 times. The only thing we're not including in there is the idea of no misses, which is the same thing as 1 minus the probability of all successes. The idea of not missing any is the idea of making all of them. So with this, we have 1 minus, we take our probability of success, and it's the idea that we'd have this 6 times in a row. So this would be a 0.7379. So there is a 73.79% chance he misses the bullseye at least once. And the rule that's coming through here is that whenever you have this probability of at least once, that's always going to be equal to 1 minus the probability of none. That's the only thing that would be excluded if we're looking for at least once. Let's actually jump down. That's kind of similar to the one up above in part A, but let's start getting to our binomial. Probability he gets at least, exactly 4 bullseyes. So now we're going to binomial because the order doesn't matter. It can just be any order, but we want to see 4 bullseyes out of the 6 arrows. So with this, we have 6 trials, and we want to see 4 successes, which means we take our probability of success, raise that to the 4th power for those 4 successes, which means failure we'd have to have 2 times to make our total of 6 trials. Now again, I'm going to show this in GeoGebra, or you can plug this into Excel, whichever method you like best. This should come out to a 0.2458. So there is a 24.58% chance he gets exactly 4 bullseyes. With part E, what's the probability he gets at least 4 bullseyes? So with the idea of at least, that means 4 is the very least value we want to see. So 4 is okay, 5 is good, 6 is good. So we want the probability of x being more than or equal to 4. And this is what I'm going to show in GeoGebra, because what you'll do is you'll build the model, and the model that shows in GeoGebra, you can shade the area that matches. So if we have our model in GeoGebra, what we do is wherever 4 is occurring, you'd shade at 4 and everything above 4 as well. So you kind of be including 4, 5, 6, and then GeoGebra is going to give you the value out. So what we'll see in GeoGebra is 0.9011 as our output. So be sure to check out that other video where I go through the steps for this. So this means there is a 90.11% chance he gets at least 4 bullseyes. If you wanted to calculate using the formula, you would just calculate probability of x equals 4 plus probability of x equals 5 plus probability of x equals 6. It's just that GeoGebra will kind of take care of that in one quick step instead of having the 3 separate formulas. And then probability gets at most 4. So with this one, 4 is the largest value that we want to have. So 4 is good, 3 is good, 2, 1, 0. So for this, we'd have x less than or equal to 4. Something you want to do is get comfortable with, if you see the word at least, it's going to be more than or equal to, at most is going to be less than or equal to. Again, within GeoGebra, you can get this shaded region for 4 and below, and that should give you a 0.3446. So there is a 34.46% chance he gets at most 4 bullseyes. So those are our probabilities, kind of using the formula, and then switching to GeoGebra is going to be a great way to get these probabilities out. How many bullseyes do you expect him to get? So there's our expected value, or our mean, and with what standard deviation. So we have our formulas on the previous, see these values just at the top of the screen. So this mean should be 4.8. Standard deviation should be 0.98. Meaning we expect him to get 4.8 bullseyes, and on average this deviates by 0.98 bullseyes. And that's our binomial model.